Welcome. We will wait
Hello.
10 minutes.
Okay, good. Yeah, I'll be back. I'll be back soon.
All right. Thank you. Would you like to try to share your screen just to test it, if it's work or not, Professor?
Sure.
No? Okay.
Yes. I just need to rearrange some windows. Okay.
Okay. Looks fine.
Yeah. Okay. It's good.
Yeah, good.
Yeah.
It's work. Uh, 5 minutes more so we can start. Okay.
Yep.
Is it okay?
No, it's fine.
Good afternoon, Prof.
Okay. Can we start, Professor?
Yeah.
Okay. Okay. Assalamualaikum warahmatullahi wabarakatuh. Innal hamdalillah nahmaduhu wa nasta'inuhu wa na'udzu billahi min syururi anfusina wa min sayyiati a'malina man yahdihillahu fala mudhillalah wa man yudlil fala hadiyalah. Asyhadu an la ilaha illallah wa asyhadu anna Muhammadan rasulullah. Good afternoon everyone. Welcome to the first webinar series on STEM education, explaining phenomena with statistics, Bayesian Method, disease mapping, and R-INLA. Thank you for taking time out and being here today. This event is hosted by Department of Mathematics Education, or Prodi Tadris Matematika, and supported by Faculty of Tarbiyah and Teacher Training, and also supported by Data and Information System Center, or TIPD, UIN Mataram. First, let me introduce myself. My name is Indira Putri, and I'm a statistic lecturer in Mathematics Education Department in UIN Mataram. I will be responsible for hosting this webinar. Today we'll be looking at the following. First, there will be a welcoming speech from the Dean of the Faculty, Ibu Dr. Hajah Lubna. And then we will have a presentation from Professor Havaard Rue. He is a professor of statistics in computer, electrical, and mathematical science and engineering division at KAUST. Good morning, Professor.
Morning.
We'll be running a live Q&A at the end of the webinar. So we have enabled our ask and question feature. It is on the right-hand side of your screen in the auditorium part. So if you have any question, just pop them in there.
Udah.
And if you miss anything or unable to join us in Zoom, don't worry, because we will also doing live in YouTube channel. The channel name will be posted on the chat forum. We have posted the name of the channel, so you are free to share it with your colleague so they can join us together via that platform. We will also provide you an attendance form that will be posted in the chat forum several minutes before the webinar ended. So please kindly check it while this webinar running. Okay, for the first part, I'm glad to welcome Dr. Hajah Lubna, who will give a welcoming speech for us. Ibu Dr. Hajah Lubna, please, time is yours.
Thank you very much. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillahirabbil alamin wal aqibatil muttaqin wa sallallahu sallama ala khatamin nabiyina wa ala jamil anbiya'i wal mursalin wa ala alihi wa ashabihi ajmain. Amma ba'du. The Honorable Vice Dean and Head of Study Program in the Faculty of Education and Teacher Training, State Islamic University Mataram. The Honorable the Speaker, Prof. Havaard Rue from King Abdullah University of Science and Technology, Saudi Arabia. The Honorable Lecturer in the Faculty of Education and Teacher Training, State Islamic University Mataram, and heavy webinar audience. Firstly, I would like to thank to the presence of greatest Allah Subhanahu wa Ta'ala, who has given us the blessing and guidance, grant us all with health, so that we can gather here in this beautiful agenda. Secondly, my peace and salutation always be given to our Prophet Muhammad sallallahu alaihi wasallam, who has guided us from the darkness to the brightness, from Jahiliyah era to the Islamiyah era, namely Islamic religion that we love. Ladies and gentlemen, personality as the Dean, I would like to welcome you all to this international webinar held by Tadris Matematika, Study Program, Faculty of Education and Teacher Training UIN Mataram. I would like to congratulate the Community Tadris Mathematics Study Program that has arranged successfully the agenda. This webinar is in the with the agenda, the faculty and university to be part of international academic community. You see, we do always support academicians to reach international recognition with the academic achievement. Also, this webinar is the real contribution of the study program and faculty, the for their talk and spirit to the development of educational in Indonesia. Happy webinar audience. We are grateful to have this webinar, which will be focused on STEM education, particularly on statistics and its application. We are also extremely glad to have Prof. Havaard Rue as keynote speaker here. Welcome. He is a professor of statistics from King Abdullah University of Science and Technology. He is also a principal investigator of Bayesian Computational and Modeling Research Group at COUS. He is a honor for us in Faculty of Education and Teacher Training UIN Mataram to have you here. So thank you very much. Welcome to all participants. We truly hope this webinar can provide you some inspiration and knowledge that enable us to bring a more mature and contextual science learning for our generation. The development of STEM education in development countries indicates that STEM needs to be promoted since is a paradigm where that created interdisciplinary learning and provides achievement results of science, mathematics, engineering, and technology. As a faculty that produces prospective teaching in math and science, aside from linguistic and region education, it is important and crucial for us to continually refresh our scientific point of view and way of thinking regarding to STEM education. Through this positive action, we believe I will create a positive academic culture, develop our knowledge as well as our student knowledge, and also create an opportunity to process a more essential STEM education research that will affect our education in significant method. Also, through discipline, come from statistics or mathematics, his experience in applying statistics to many scientific phenomena will give us a valuable revelation from perspective on pure science on how exactly statistics can be used in explaining some nature phenomena. This webinar on STEM education proposed by Tadris Mathematics Study Program in Fiona that can be followed along with another similar webinar or conference so that we can build a strong confidence in supporting all students with meaningful knowledge and skill. Ladies and gentlemen, by asking Allah Subhanahu wa Ta'ala blessing, we open this webinar STEM education by reading Basmalah. Bismillahirrahmanirrahim. Thank you very much for your attention. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Ibu Dr. Hajah Lubna. Thank you for supporting us. And now, here is our special guest, Professor Havaard Rue. He will presenting what he is doing with his research group in COUS. So we hope his experience and his knowledge will give us some insight about how statistics can be explained, can explain a phenomena in our daily activities. So we hope it will give us a valuable meaning. Please, Professor Rue, time is yours.
Thank you. Let me, you need to allow me to share the screen.
Yeah.
Yeah. Okay.
You want to share your screen?
Yes.
Yeah.
No, it's fine.
Yeah, it's good.
Very good.
Yeah, you're good.
Okay, thank you so much, and thank you for this invitation. So this is approximately the title. Let me, oh, sorry, I just need to put the pointer here. Okay, so essentially, where is KAUST?
Mm-hmm.
So KAUST is on the just north of Jeddah. It's just on the shore of the Red Sea. It's a quite new research, essentially a research-only university. So mostly doing for students doing PhD. Opened in 2009, and it's very small. Okay, so now it's about 1,200 students, 450 postdocs. About, I think it's these days about 180 faculty. So it's tiny. And there is like a small international community living at KAUST. So it's like a small bubble, almost like a holiday resort for research. Okay, so we're all living here. And of course, if you have the talent, everything is free. You even get paid to come and study here. You know, all of these, it's amazing conditions. So I just, if anyone is interested, you can contact me. Okay. Yeah. So about this talk, Indira provided with a tentative title, which is kind of easy because it's kind of set the scene for what kind of you could have, what you want to kind of expect. So it's about Bayesian method, disease mapping, and R-INLA. This is essentially centered around everything that we're doing here. It's kind of set the scene. So it's like, why Bayes? I'll talk a little bit about that because there are many ways we can kind of argue for this, and these other ones. Okay, we get there. Okay, we talk about R-INLA, which is our kind of main big project that I'm almost been working on last 15, 20 years, you know. So this is like the thing we're doing, and it's there are still major development. Even the last couple of months, it's like, yeah, okay, what sorry. Disease mapping, I try to integrate it, but it's a rather large field. So there will be some smaller examples, but sorry, there is no time in this talk, so I was not able to do it. But there will be similar examples. Okay. So in short, all this kind of give a nice summary for what we're doing here and that the research group is doing. I say research group. The point is that here at KAUST is like there is no department in the normal university sense. You only have a PI like me, and I'm creating a group to work on my stuff. You know, and this is how this university is functioning. You get PIs, and they are doing what they want. So this is how it's working. Okay, So essentially, we talk a little bit about philosophy, about statistics. So what are statisticians doing? Like if you, short answer, you analyze data. What you want to find in data, you want to extract information in data. What is information? This is the information you find useful. Okay, what you want to kind of, there is always some kind of built-in randomness. Okay, noise, if you think noise term, you want to get away with that. Beyond buried in the data, there is also this signal that is not noise. Okay. So what we do, we kind of process data, and very often we kind of collect new data and we process again. So what we're doing,
Professor,
point is that, yes?
I'm sorry, have you slide your screen, or you haven't slided? Because
I have shared my screen.
no, slide. Have you? I mean, I just look at your cover here, not yet your material in your share screen. Do you know what I mean?
No, sorry, I'm totally lost. So it doesn't work?
It works. Your screen is there, but it's still the first part of your screen. Have you removed it or not yet?
No.
No.
So okay, let me stop.
Yep.
Is this better?
This is Y bias slide. Yes.
And now it's still okay?
Yep. Thank you.
Okay. You want me to go back?
No. Just.
It's okay.
It's okay.
Okay. Sorry. So you didn't see my previous slides as well, huh?
Yeah. Yes. I think you haven't removed it yet.
Okay. Yeah. So this you haven't seen, huh?
Yep.
Okay.
Thank
Okay. Sorry. Okay. Sorry about all this. There's some technical glitches about how things are working. Okay. Again, this is a picture of CAST. Super modern campus. Yeah. So again, set the scene for the talk. You talk a little bit about Y-base, and then talk about this R-INLA project. Okay. So what are we doing? Analyze data, process information. The point is that the information we want to kind of extract from the data are already there. You know, we want to kind of extract it, but we have to kind of balance everything. We have to balance like the signal from the noise, and very often we're doing this in kind of how we process data, we collect new data, we process again. Okay, so we are in this kind of infinite loop of always kind of doing information processing. Okay. Very naturally, we want kind of to put up a kind of a balance between what we kind of put in and what we kind of get out in terms of information. Okay. So we have information and data. Some of these we can move some of this information that is in the data to the kind of essentially to the model, and kind of take that the remaining information and move it to the noise part. Okay, so it's always this kind of balance. So there is certain information we just need to know how we want to kind of what is model and what is kind of noise. Okay. If you look at this thing, there must be at some point a kind of balance. So so what go into the analysis, how to come out, is just being transformed. Okay, this is like the balance of energy, you know. In applied math, there is a balance, or very often balance of mass. So what all the mass that goes into a small element has also to come out, you know. There is always this thing. You cannot add and subtract things. You can just take what is there and move it around internally. Okay, is this noise or is this part of the model? Okay, and this is the core of this information processing, and this is essentially the requirement for any kind of good. This is like the definition of the information processing group. If we define what we need, what we mean by information. Okay. There is a super nice paper, American Statistician 98. No, not 88, sorry. 88 is just four pages. It's super short. This is one way to kind of explain Bayes. We can make this kind of formal. So you look at any kind of rule that process information. You set up definitions for what information is. This go back to the Shannon entropy and this measure of information. So it's all about the log density, the expected log density of the -1. This essentially lead to a variational formulation around what variational in the sense that if you're not doing it correct, you'll either add or subtract information. If you get it right, you have that the input is the same as the output. It's just take different forms. Okay, so what do we have as input? Input is essentially what you have learned from the previous experiment. If you're thinking that we're doing this kind of continuously. So what you think, what you have in is like what you got out of the previous experiment. So this is essentially this kind of prior for the parameter. Then we have the likelihood. This is the information that comes in. What comes out is a marginal likelihood, it's a probability for data, P of Y, and also the updated information about the parameters in the model, pi of theta given. If you look at this purely from an information kind of balance, no probabilities in this kind of, you don't use the rules of probability, you know, in this kind of sense, you end up with Bayesian. Okay. So it's the only rule that process information that doesn't add anything and doesn't subtract any information. Okay. I talked about the variational form, and this is super exciting. Yeah. So what is the variational form? This is a little bit technical. Okay, so we want. So this is a function of a function. Okay, so it's a function over a kind of think posterior distribution. If we, it's not really there, but we can think of that to make it easier. So the first term here is that we have to balance the expected log likelihood. Okay, not the log likelihood, but the expected one. The expected is over the posterior distribution. And we have to balance this with a distance from the prior. So it's all about balancing what the information that is in the data and the information that we had before. Okay, so this is very, very natural. Every time you meet some new information, you balance this with what you know from before and the information that is there. And usually you go somewhere in between. Okay, the only point that somewhere in between is in between in some kind of space. This is a bit technical. If you kind of minimize this one for all kind of well-behaved densities, you end up with Bayes' theorem. Okay. This kind of form is also very exciting because this is in machine learning. This is known as variational inference. This is the backbone of variational inference, even though it's not kind of often sold this way. This is something that is behind this thing from the very basic, even though this kind of the roots have been a little bit forgotten the last in the last year. So this is what inherently is behind this kind of inference. Okay. Yeah, is just pre-announcing. It is coming soon as a huge paper about. You can essentially derive most of these standard, all these state-of-the-art learning algorithms that is used in artificial intelligence and machine learning, all these things, from essentially this equation. And there are some other things. Yeah, so it's again, it's very central. If you cannot compute posterior distribution, you can compute approximation using this variation information. Okay. Okay, so that's one argument why we should do things the Bayesian way, simply because it's a way to kind of process data. Process data in the sense that it's in a way to ensure that we don't add anything artificial or that we essentially forget any information that is there in the data. Okay. Again, we go back, and now we go back to the kind of main core for what we're doing here is the R-INLA project. Okay, so it's not formally a project, it's more like an umbrella for related research activities that all kind of have a common goal. Okay. There is a webpage, r-inla.org, that you can visit. That contains links and all this information that you need. Okay. So the rest of the talk, just to give an overview and discuss some things that we kind of work on. Okay. So what is it? It's essentially an R package. It do what's called approximate Bayesian inference. So it's do this Bayesian inference for a very specific class models. This is a class model that we have that is called a kind of latent Gaussian models. It seems very, very restrictive, but it's not. And there is an interface in R to define, analysis, and evaluate these models. You might think, oh, this is just R code. No, this is so much development, you know. So all this is tied up with method development. So all we do with methods would also end up here, you know. So this is a very active kind of project. The good thing is you can do things very quick, okay, even for large LGMs. And we're talking about models with kind of some millions of nodes. So we can do this on a big computer, high accuracy. So we get very close to the true posterior distribution. We can do very complex models in this framework, even though the setting seems super, super naive. You know, we come to that next slide, I think. The point is that this kind of class model that we are working on is essentially all the important, most of the important models that we're doing are within this class. You know? Has a very good setup or support for spatial models, because that was a hurdle, so we had to deal with this as well. If you're doing kind of applied advanced statistical work, this is very, very convenient software. And a lot of things that wasn't really practical before we started with this. Now it's kind of easy and routine, even for non-specialists. So what is a Gaussian model, latent Gaussian model? Okay, what is it? Is you have some data. This is encoded in the likelihood. Okay, so y is a data and x is essentially something Gaussian. Then we have something Gaussian, and we think of that Gaussian as, okay, we come back to this. We would like this kind of graph structure in this Gaussian. So not just any, but we come back to it. You have something Gaussian. It says here Gauss marker random field is a very fancy name for something Gaussian with some additional assumptions. And then we have some what we call hyperparameters. These are usually variance terms, like variance, precision, correlations, like anything that is not naturally Gaussian. Okay. The point is that the cases is that we don't have that many hyperparameters. The theta here is a small dimension, 2, 5, 10, maybe 15. Is in this range. X is a Gaussian that could be huge. 1,000, 10,000, 100,000. We can have a million. Okay, so this is huge. The data is what it is. It's usually terms of 100,000 or yeah. They are what they are. Okay. So from here, we want to kind of compute what's called marginal distribution. We want to compute the effect of each term from this model. So we have to kind of integrate out all the remaining terms. We're doing this by using something called Laplace Approximations, but we're doing this in a 2 layers, a Laplace over Laplace, then we integrate them out. It is a bit technical. Okay. So what is here? Essentially, all these models is additive, generalized additive, all these kind of models, measurement error model, spline smoothing, regression, functional data, disease mapping. All these models for disease mapping is there. Kind of, you have this point process model. This is what's called log Gaussian Cox process model. It's like a Cox process, Bayesian Cox process model. You have this more spatial model. This geostatistics, the Gaussian fields, kind of thing. We come back to these later. We have models in space and time. We are doing a lot of work now on survival models, and especially joint survival model, competing risk models, all these things. They all come under this kind of framework. It's amazing, you know. And so this way of looking at the model as a latent Gaussian model, it's very useful for doing the computations. It doesn't help you doing the modeling. It doesn't help you describing the data and tell you what to do. But if you know what to do, if you can frame it in this framework, we can do the computation for you. Okay, so this is kind of setting. Just to give you an example, here is CDC, Center for Disease Control and Prevention. This is a kind of the U.S. main health institute that give all the advice for COVID and health in U.S. Andre, is there a question? No. Okay. Yeah. So they produce table. This I think this came last year about excess steps that do data analysis for the whole US, and they use this kind of software to do this analysis. Okay. Just an example, they have done a lot of analysis using our software and method. Okay. All online prediction guidance, like country like Brazil is also using this kind of software methods for doing this. Just COVID-related research. I counted just yesterday about 140 scientific reports using our software to do analysis of COVID. Just, of course, last year. You know. Okay. Let's see here. Okay. So it's all about properties and connections to the essentially the multivariate normal. You might think the multivariate normal distribution, yeah, we know everything that there is to know. Yeah, but yeah, okay. It's not so simple. What is a correlation? What is the concept of correlation? Okay, so if you have two random variables, zero mean, some unit variance would make it easy. Correlation is just expect the value of the joint, okay, the product. Okay. The whole concept is late in 1800. It was invented according to regression. Okay. It's described linear dependence only. Okay, so you have this kind of, so how close they are to a straight line. This is the degree of correlation. But you can have other types of dependency, of course, that is not linear. And you can have zero linear effects. So these are zero correlation, even though you see that they are dependent. Okay, so this is a feature. It's not an error. This is the way it's kind of constructed. Okay. If you go to multivariate, if you have a random vector, we usually write this is a multivariate normal. Okay, so we have this, it's called the covariance matrix, which is the matrix of all correlations. Okay, so it had to be symmetric, positive, definite. Sorry, it's coming here. Okay. This is the normal way that normal multivariate normal distribution is described. This is fine. It's fine. It's not very interesting. Okay. The interesting part is when we come to what's called conditional independence and conditional dependence. Okay. This is now we're talking. Okay. This is related to a graph representation of something multivariate normal. So you can talk about the joint distribution of two nodes given the rest. So here, essentially, you see you have nodes A, B, C, D, they are connected. So this is how the dependencies, so A and B are connected to D, that again connected to E, that is again connected to C. That also makes A and C connected because they have a path, okay? You might also guess that if we kind of block, you see this pointer? Yeah.
Yes.
Yeah, okay. So if we kind of block node E, you will see that if we condition, this is like conditioning. If you condition on E, then C and D will be independent. Okay. So the point is that if we have conditional independence, then it turns out that certain elements in what's called the precision matrix, which is the inverse covariance, is zero. And this now we're talking, this is now it's getting interesting. Okay. So a point that all these connections you see in the graph, they represent non-zero elements, not in the covariance, but in the inverse. And if there is no edge, like there is no edge between B and C, it means that that interaction term is zero. This is super. Now we're talking. Now it's getting practical, okay? Because we're describing dependence not by the dependence, but how is more a constructive way to describe dependence. And then we have to compute the dependence. Okay, so we're not modeling the covariance. We can model the inverse covariance, and we can compute the covariance. You have seen this before. The point is that this is not very clear in the literature. Okay, you have this autoregressive process. So what happened at now? The mean is almost what happened yesterday plus some noise. Okay, so you have xt is like a time series in time with some coefficient. What happened at the previous time point plus some noise. So what you see here is that this is not the covariance matrix. This is the inverse. It has a tridiagonal matrix, so it's almost zero. Okay, but if you compute the inverse, it's a completely dense matrix. Everything is dependent. But since you only have interaction between pairs, you have the inverse matrix is almost zero. It's very, very sparse. Okay. Of course, you can make this properly. This is like, it's called a Ornstein-Ullbach process. It's a continuous time process. It's a Wiener process. Okay. The same thing, we could use the same thing when we're building kind of regression model. You have a classical regression models. You can generalize it. Instead of having a linear effect of a covariate, you can have a smooth effect. You see here, it's like instead of a straight line, you have a smooth line. And this F here could be a Gaussian process with these kind of properties that we have talked about. And you can mix these with non-Gaussian data. So this is one of kind of prototype for these latent Gaussian models. You're kind of building up things using Gaussian components, you put them together and you mix it with some data. Okay. The thing is that if you do the math correctly, you can maintain sparsity structures. Okay, so this is on the right here. This is like what you get. This is not the covariance. This is the inverse covariance. Okay, the point is if we work with the whole model, all the components, and also the sum, the eta is a linear predictor, then we essentially end up with an inverse covariance matrix that is very, very sparse. And this is what you see here. This is almost zero. It's like this has this matrix is n by n, but it has only order n terms that is non-zero. Okay, it's a very sparse matrix. So why we like sparse matrix? Because it's faster to compute. This is the whole. This is essentially the whole idea. Okay, faster to compute because essentially we don't have to compute zeros. If we know something is zero, we don't need to compute it. And this is how this idea works. So that's why we can do things in very high dimension. It's going very, very quick because we can make use of this kind of structure. Here is another sample, more spatial data. Now we're talking about more disease mapping. This is like more a point process data where, yeah, it's like a spatial survival model. We can use Cox proportional hazard models. So we can overlay this with a triangulation of this area, and we can define what's called a Gaussian field on these triangulations. And what are these triangles? These again represent these nodes in the graph. So this is say who is connected to who. We can do this. We end up with kind of a matrix that is looking like this. Okay, again, very, very sparse. So we can do computations on these sparse objects. Of course, this relates back to, if you're coming from applied math, this relates back to applied mathematics by solving differential equation or partial differential equations. So if you have an operator L, you can apply it to a function and a process xt, and the right-hand side is essentially Gaussian noise of certain type. Then you can compute a numerical approximation using like finite element method, and what you get is that this precision method, this inverse covariance is A transpose. Okay, so this is how you can kind of build up these kind of models. So for example, a first order random walk model, then we are essentially connecting back to these autoregressive models. If you do that, use a first order difference, you get a first order difference square, and you get this kind of matrix. Second order random walk, you get this second order root matrix, and so on. You can go properly on these differential equations, and you connect to what's called the Matern model in spatial statistics. It's Gaussian fields with certain covariance structure. But instead of thinking about covariances, we're thinking about the underlying process. Then we can work with this. The point is that you can work with this. This is much harder. It's very, very much harder. But if you have the tools, if you've done the work, you've done the trunks, you know, you have done the groundwork, then the point is that a lot of things that is almost impossible to do well, it becomes super easy. We can do this on the sphere super easy. It's just to take this PD and just wrap it on a sphere. We can work with non-stationary models. We can have models, all the computation properties are already done because we are working on this sparse representation. We can do it with boundaries, we can do it with these barriers and obstructions. Everything is becoming super, super easy. Okay. Here is another, so that's how you kind of build up models. And here is how can you do the inference, okay? The point is that we have a model that is almost Gaussian. If you have no data, we can kind of compute the solution, okay? Because everything is Gaussian. You have some variance parameter, but if you condition on those, the rest is Gaussian, we can compute this. The point is when you have something that is so much Gaussian, the also posterior distribution will be in the neighborhood of something Gaussian. And then this very old idea come to mind. Of course, this is like what's called Laplace Approximations. So what is this? It's essentially by approximating anything with a Gaussian. So what's the justification? The justification is you want to kind of compute the integral of this type. Integral of exponential n is something that you want to go to, that we want to send to infinity to do some math, okay? G is a well-defined function. Well-defined, these integrals should exist. This must be function that allow this integral to exist, you know, has a mode and it go to zero, go to minus infinity, okay? So if you find a mode and you do proper normalization, then what is this integral? You do a second order expansion, you get essentially something Gaussian, and this is just a normalizing constant for the Gaussian. Okay. Of course, when n go to infinity, it means that the variance goes to zero. Then essentially you get a spike, and the error must go to zero. Okay. The point is that you, in this case, you have a relative error, is 1 over n. And this is much better than the error we have in the estimation, that is 1 over square root. Okay, so it's already much better. Okay, here, I'll just give you an example how this works. This is kind of a logistic regression example. We have x is dimension 2. We have 2 observations that are both 1. And this is logistic regression. So this is the second part here. This is the likelihood term. So they say that the first data point is essentially 1. They say the second data point is essentially 1, and these are kind of correlated. Okay. So this is the marginal distribution for x1, essentially given the data. Okay, forget about it. How can we approximate this? Yeah, we can do this integral. Is it dimension 1? We can do that numerically. But if you want to use the Laplace approximation, then how do the computation goes is like you choose a value for x1. For x1, you will optimize this function with respect to x2. At this optimum, this mode, you will find also the curvature. With the curvature is the second derivative. The second derivative is related to the variance. Okay. And then you have the variance that gives us a normalizing constant. Okay. So for every value of x1, you have to do an optimization. At the mode, you have to find the curvature, and then you can do this. And you do this as a function of x1. Okay, this is how the computation goes. This is essentially, if we instead of doing it as a function of x1, let's just find the mode for the joint and approximate that with the Gaussian. And then if you do that, then you essentially get this one. If you do this Laplace approximation, you will get something that is a little bit different. If you do the true integration, then you get essentially this one. So it's almost doing, you see, it's almost doing the correct thing. Now we can kind of tweak it to a harder case. This is the same, this is joint approximation. Here is what the Laplace, so that will be slightly, we are slightly more off. And then you see that compared to the truth, we are almost there. There are some slight differences here, but already this case here is essentially far beyond what you will see in practice. Okay. It's just that in this simple case, we can do insane cases, you know. So this is a totally insane case. Okay. It's just before the kind of all this integration technique kind of breaks down almost, you know. So this is what you get for Laplace approximation. It seems very odd, you know. And this is the truth, you know. But even in this totally insane case, is doing very well, you know. But the normal case will be this one. Okay, and this is what you see in practice. So that this is also what you see, that kind of the approximations that we kind of compute is more or less what you'll see if you're doing extensive MCMC. Okay, even this case here is almost you don't see. This is a total. This is just insane. So all these kind of tools is kind of built into this package that we have. Is a huge one, and there are several books about this as well. We've written one. It's about SPD models. There is one. This is from two Italians. There is two from US. This one we did. This is with Paula Moraga. Sorry. This is a colleague here at CAS. This is more, and this is exactly what you want. This is like the disease mapping, analyzing health data, the spatial mapping of health data in space and space-time. There is also an introductory book by Virgilio Gomez from Spain. Both these two books, the SPD book, is more about how do you deal with these spatial models. And this one, this introductory book, they're also free online. So you can read them online. So there is what's called a Git book version that is available. So this is, you can read it in your web browser. All the code is there. Everything is made available. Okay. And this is also the case for the whole project. It's like all the code we do, everything there is available here at GitHub. You know, so it's all the code is available, everything is open. You have, there is extensive use of all these things: statistics, biology, ecology, health, especially these kind of areas, is super. It's a lot of use. So this is the book that we had like almost 2 years ago. Yeah, it's a long story. It's a very special book. There is still a lot of development. It's like now we are kind of redoing the internals, or redoing how we kind of look at the models. We are doing approximations in another way. It's very exciting. So we're building up a new code base, a new way of doing these things. Of course, this is colored by our kind of 10-year experience with these kind of approximations. So we can do it faster to do the important corrections. Part of this thing that I haven't talked about is like how to think about priors in this kind of context. And it's at some point in some years ago, it became clear that the normal kind of suggestions about how to think about priors in this kind of context didn't make much sense to us. So we had to develop our own kind of framework. It's called penalized complexity priors. It's essentially about how to think about priors in these kind of models, unless you know exactly what you're doing. Okay, so how to think about priors in situations where you don't have precise knowledge. The point is that you have to release yourself from the concept of parameters. Parameters are just confusing because we think we understand them. We think we understand the impact, but we don't. So it's very nice. It makes very much sense, and we use it all the time when we can. Okay, so this is another talk about priors. New developments, quantile regression. Quantile regression for health data where the outcome is discrete. We can do. There is a lot of work towards a joint model in survival analysis. We have new people coming in with expert knowledge in survival. This is very exciting. That would be, I think, that's a big thing. Skew probit regressions. There is a lot of activity going on towards high performance computing, because it's not only about statistics, it's also about computing. And why is computing important? Simply because we want to do it faster. And we want this to kind of scale better on kind of machines that has many cores. So we have servers, we run a model usually on many cores. We talk about 50 cores, we can just fill the machine and run it. And you can only make use of this if you kind of do the proper coding for doing these things. The end of the story is it's kind of this latent Gaussian models. This way we kind of think of this is enormously useful class of models. It's a lot of structure, has good computation properties because it's connect to kind of computing, like factorizing, solving equations with sparse matrices, and they're all kind of symmetric, positive, definite. It's very, very convenient. And most of the models that we're interested in are in this class. Or if they are not in this class, we are not interested in them in a way. And then there are someone else's problems, not mine. Again, all the software, everything we do is you find links here. So all the code is open, all packages, everything is all there. So I think that's it. So thank you. Thank you. It's a very brief introduction. I'm sorry, the amount of material behind this is enormous. So this is very, very, very brief. So if you feel that details were left out, yeah, there are simply too many. Yeah. Okay, but it's an introduction. Okay. Thank you so much.
Thank you. I think we will have a Q&A session, Professor.
Yeah, sure.
Do you want me to read the question, or do you want everyone?
I see something in the. Yeah,
it's in English.
I don't know where they are. So please.
Yeah.
Yeah.
Do you mind if I talk in bahasa for the participant?
No. Yeah, you do what you want. Yeah.
Baik, rekan-rekan, kami persilahkan jika ada yang ingin ditanyakan. If you have any question mengenai topik yang baru saja disampaikan oleh Profesor Rue, kami silahkan bisa ditulis di chat atau bisa juga disampaikan secara langsung. Kami persilahkan, mumpung profesornya menyediakan waktu untuk berdiskusi dengan kita. Silakan, ada yang ingin ditanyakan? Any question? Okay. While wait for other question, do you mind if I?
No, please.
So you said that INLA or GLM or latent Gaussian model is way to compute, right? Way to compute some models.
Yes.
Yeah. So and if we want to understand about priors, it is related to Bayesian, about priors.
Yes.
We have to release our knowledge about parameter. Is it right?
Yes.
Yeah. So can I say that Bayesian method or LGM is another way to model a situation, or because what I know is I work in Weibull distribution, and I work in estimate the parameter of the Weibull. So is it another way to approach the phenomena, or we can it can be work together, bias and modeling situation with a distribution? What do you think? But
okay, yeah. So it's like this kind of statement is that it's a way to compute, not a way to model. Is that it's the intuition was that you should care about the data and the model and do what you need to do. And if these turn out to be or can be written, or rewritten, or re-expressed like a latent Gaussian model, then you can do the computations. But we don't kind of start by thinking, oh, let's invent the latent Gaussian model. So it's more the way that you should always care about the data and the model first, and then if this happens, then you can do it. Because some of these models, like these Cox proportional hazard models, it doesn't look like these things. Yeah. But there exists, like you can re-express like Cox proportional hazard as a Poisson regression. Mm. You can do a data expansion, and you can get the equivalent form using Poisson regression. And the same thing we can do with these log Gaussian Cox processes. We can formulate them as a Poisson regression, is it differently, and then be able to do these computations. Okay. So some of these models will need a kind of rewrite because they don't look like this in the first place. And that's why we're thinking of it's like, because, okay, let me go back here. Is this all of statistics? You have something Gaussian that you observe with some data and you have some parameters. Is that everything we do. This kind of model formulation seems simply too easy. It's like you look at it and it's almost like a joke, you know. It's like it cannot be that simple. It turns out that in most cases it is, you know, but it's not represented like this. It's not sold like this. It's not explained like this. It's not interpreted like this. But you can kind of put that in these frameworks. And then as soon as you put it in that framework and you have kind of general code that attack this, can solve this, you can do the analysis. So that's the point, you know. But very many cases you don't see this formulation at all. It's not represented, it's not sold as this at all, you know. So that's why we see this is more it's a way to do the computations. It's a bit abstract formulation. It's kind of related to these kind of mixed models, but it's not directly related. It's more general than this. So this is the thing. So even if you think you're working with Bible and these things, then you can also represent the model in this form and make that to do the computations. We're talking about priors for the variable. You have this important parameter in the exponent, you know. So how do you go around thinking about prior for this one? It's super hard. You can do the math. We have done the math, and you can derive kind of the good prior that do contractions to the simpler model. The simpler model in this case is the exponential. Yeah, so this is how it relates to this kind of priors. Instead of thinking about parameters, priors for parameters, we're thinking about distance between distributions. And we put the prior on the distance, and then we can do a change of variable go from that prior on the distance to prior on parameters. So this is how we think about priors.
Thank you.
Yeah.
So we have two questions here. The first is how to reduce a bias in a data. No, this is not bias, but bias. You know.
How do you reduce data in?
How do you the bias BIAS?
Yeah. So how do you reduce bias, or how do you debias?
Yes. How do you debias the data?
Okay. Yes. So debias, if you're doing kind of classical frequentistic statistics, you would have estimators. You want normally them to be kind of unbiased.
Yeah.
Yeah, and we want to kind of, if you have an estimator, you want to kind of estimate the bias and subtract that to get something that is more or less unbiased. In the Bayesian context, there is no concept of being biased, unbiased. Okay, by construction, you're being biased because you're using prior information, you know. So there is no concern about this being biased. You'll always be a slightly kind of biased in that sense. On the other hand, there is in the Bayesian context, the parameter is a random variable because this is how you kind of model the knowledge about the parameter. So there is no kind of one value for the parameter you can be biased against. So it's all this kind of unbiased thing. It's that kind of concern is no longer there, you know. So that kind of makes it easier. But I think also a lot of this unbiased thing, it's often for me, a lot of this is very confusing. We taught in the basic courses, you need an unbiased variance estimator for the variance. No, we don't. The point is that the variance is a scale parameter, and you don't want to have an unbiased estimator for the scale. You want to unbiased estimator for the log of the scaling. Okay, because the scaling is a scaling parameter, it's not the additive thing. So it's like 1 over, is like you want, because the expected value of 1 over x is not 1 over the expected value. Okay, so scale parameter has a very different thing, even though that in the basic courses that is treated like any other parameter. So no, the distribution for the variance is skewed. Since it can go very high, you have to account for that by having an estimate that is too low. You know? So it's very skewed, and you know you don't want this parameter to be unbiased. It doesn't make sense. But still, they all the theory is about unbiased estimators and all these things. So yeah, so I'm not very concerned about unbiased estimators, you know. Sorry, but in the Bayesian context, the whole concept, there is no concept of unbiasedness. Okay, because it is not relevant in this context. Okay.
I will try to translate your answer, but let me stop for half a minute because we have a adhan here for our prayer time. Would you mind? Just 30 seconds. Thank you. Baik, Bapak Syamsuddin Sirah, semoga keterangan atau jawaban dari Profesor Rue sudah bisa membantu Bapak untuk mendapatkan jawaban mengenai kebiasaan atau bias dalam data. Pada intinya, beliau ingin menyampaikan kalau dalam kasus bias, metode bias, bias atau tidak bias dalam data itu tidak menjadi concern, jadi tidak menjadi prioritas karena datanya dibiarkan pure begitu saja, gitu. Untuk kemudian dimodelkan dengan metode bias. Sedangkan kalau bukan di konteks Bayesian, kita bisa meninjau atau memperbaiki bias data itu biasanya dengan memproses lebih lanjut, Pak. Ada nanti biasanya ada tools-nya untuk melihat apakah data kita bias atau tidak. Untuk kemudian kita ingin diapain dulu nih datanya, gitu. Kalau misal kita ingin tidak dibiaskan maksudnya, maka nanti kita bisa masuk ke tools berikutnya. Kira-kira seperti itu, Pak Syamsuddin Sirah. Terima kasih atas pertanyaannya, Pak. All right, we have another question. Professor, do you mind? Sorry.
Okay, fine.
Another question is, do you mind to share a recent development of how we can applicate the Bayesian method, specifically in COVID-19 spread, the COVID-19 disease, the spreading of.
Okay. Yes. I don't have any particular. No, I've just seen people using it. I checked that the user software. I haven't been looking up specifically to to the models itself. So I don't have much knowledge of this. I try to, I try to not getting into too much involved. You know, the COVID thing is enough depressing as it is. You know, so it's like okay, other people are concerned about this, but yeah, it is out. I don't have detailed knowledge. I'm just seeing that people are using it, but it's all about the main thing is basically the same. It's always the same. You have observations, often count. You have count data. You have underlying smooth trends that depends on covariance. That's the kind of basic problem. You have the same thing. You have spread. You have spread usually in space, in some kind of So what happened if the neighbor county is highly infected, there is more likely that your county will be highly affected next week. You know, so you have this kind of neighbor dependency structure, and this is kind of basic. And you're doing this often as a function of time. So this is the basic processes, and it's kind of more or less the same, no matter what kind of data that you have. It's just, in this case, there is a bit more kind of directional effect, I guess. So, but still, these models can be useful because they are data driven. And then these small things, these kind of details can be left out. So I guess this is the thing. You want to kind of compare estimate in many different regions. How do you do that? You use a hierarchical model. So what happened here and happened here are not the same, but they are similar. Similar in the sense that they are essentially, they are both children of the same parent. Okay. So in this way, they are dependent. So this is a basic idea how to build dependence. You don't build dependence directly through correlation. You build dependence by making two children having the same parent, and then you say you don't know the parent. So this is another way to construct correlation, by having two children with an unknown same parent. If you integrate out the parent, you get correlation. Okay, so building this structure with this hierarchy. So what happened here and here is not the same, but it's similar. Similar, how do you define similar? Similar is that there are both children of the same parent. And then you can go on these different levels of the hierarchy. In this way, you have this, you get this hierarchy. This is the whole concept of this hierarchical modes. Yeah, so that's another thing. I could talk about this another time. Yeah, so this is the thing is you don't. Okay, let me see if I can. Was it here? No, okay. Yeah, I don't have that here. Okay, but yeah, I need to get some other slides. Yeah. So the point is that you can think of correlation is not about A and B is being correlated. But you think about correlation that A and B are related. So think of two children in a family, you know. If you know the parents, every kind of offspring is kind of independent. But if you take away the children, take away the parents, you integrate them out, then two children becoming related. they're having certain features in common, you know. And this is why so they becoming correlated, even though if you given the parent, they are conditionally independent. So this is how you kind of build correlation. You can think about correlation for these hierarchical structures. Yeah, so that helps me at least, you know. Sorry, the microphone is off.
Can you hear me?
Yes.
When it comes to priors, what do you think become a priors in COVID-19 spread? You know, when we will do a Bayesian model, we have to know the priors, right? The prior distribution.
Yeah.
So
what do you have in for if you're thinking of analyzing COVID-19 data? What do you have? There are two concepts. One is that you have a natural basic assumption of a simpler model. A simpler model can be this R number is 1. That's a natural reference. So you want to kind of model. If it's above 1, you want to do a contraction towards 1. If it's slightly below 1, you want to contract towards 1. So that's a natural base model. So this is one, if you only look at that model itself, if you're just estimating R. The other way is that you look at similar studies in other regions, even though it's like not the same region you're in on the same data, the information about how this, let's say the R number depends and develop, might still be relevant, you know. So you can kind of build the prior from previous studies or similar studies in other areas. So these are kind of two ways you can do it. So one is kind of go actively out and see what other people are doing, like previous study, different regions, different countries, this kind of thing. The other one is kind of to look at, don't do that, and only look at what will be a natural, simpler model. Simpler model when it's like the disease spread is like at this stationary point. It's an unstable, you know, you only infect one other on average. So R number is 1. So it doesn't grow and doesn't go to 0. So this is a natural kind of the simpler case, even though it's unstable. And you can define priors by doing kind of contractions towards simplicity. Okay.
Thank you. Oh, okay. There's another question here. Do you mind if I read it? One question.
No. Yeah.
No? Okay. How can is it possible for UIN Mataram to have a joint research at KAUST?
To have
joint research. Joint research.
Yeah. It's always possible to have joint research. But again, it depends on the level. There is always opportunity for talent people to kind of, you can come visiting here, like for a shorter period. You have student visiting programs. We have visiting programs for potential students, all these things. It's very easy. You don't need any funding. Everything is paid for from here. So if this is interesting, you can contact me and we can make this out. This is the easiest way to kind of do. It's always a bit hard to do direct collaboration online. It's always a good, if this happens, it's always better to have a mix, you know, with in-person meeting and some collaborations. But also, yeah, we have also visiting student programs for a student that is already doing like a PhD, or they want to apply, they want to come for a master, or potential new students, either for a master degree or for a PhD in the PhD program. So all this is standard procedure. So this is all possible. And again, everything is funded from here, so you don't need to worry about these things.
Thank you. Thank you. Maybe the last thing, because we have here in UIN Mataram is an education science, so that's why we use the theme STEM education. Do you have any advice for us as a place that produce a prospective teacher in science? Do you have some suggestion or advice for us about how to deliver a course, a basic course in math or in statistics that can build a good understanding for our student, so that they can have a intuition about, oh, I can use statistic in here, like not really just like compute something, but they can explain what can I do with statistic. Do you have any idea for that?
Okay, yeah, and that's hard. It's certainly much easier nowadays than it was before. It's like before when I was young. It's like a long time ago. And then if you couldn't do it with math, you couldn't really do it. Nowadays, you have this opportunity, at least within the Bayesian framework, to essentially, you can focus on the model. You can do things that you didn't thought was possible, because you have these automatic tools for doing the inference. You have the inference by doing this markov chain Monte Carlo, all these kind of methods, and you have like R-INLA for some of these methods that simply really simplifies things. So you can kind of focus on doing the modeling, doing analysis of data without worrying about how do I estimate these parameters in the model. And this is certainly being very helpful. We have here like a basic course in Bayesian statistics, and there is we're doing kind of 30-40% theory, and the rest is kind of applications and coding and doing projects, So it's much more about exposing students to problems they suddenly can solve very easily, that before the course they couldn't imagine that they were able to do this, and nowadays this is indeed possible, because you can separate the inferential part, how do you estimate and how do you fit the model to this data, from actually thinking about the model. So it's suddenly much easier today, and this is what we're doing here, And many students get this kind of eye-opening things, is this really possible to do? And you say, yes, of course. And when they have done it and seen it, then they agree, yes, we can do this. It's really possible, because you can focusing on building up these kind of probabilistic models, and you have tools for doing the inference, and you don't need to worry about, let me derive an estimator. This step is done automatic. This is already done. You can worry about modeling what you need to do, So this is much easier today, but it's required this kind of you have to design courses, and you have to do the courses with kind of a bit this in mind. You're doing some theory and then project application. This is what you do here. So the students hand in huge reports about data analysis. They're doing this kind of stuff. In the beginning, they do this by hand, in the sense that they code up algorithms themselves for simpler problems, which is good for the understanding, to build understanding. And later on, we're using kind of ready-made software for doing the analysis, because then it becomes a bit too time-consuming. So it's more to be expose them to all these things they suddenly can do, but they had no imagination that they could do it. So I think nowadays these things are suddenly much easier than it was before. But again, there is always this balance between theory and applications. So I think in need kind of both. You need some understanding of the key concept. You need to kind of do some kind of basic coding to get the understanding, you really understand them in simpler cases, and then be able to use the software that we have to kind of to be exposed to more challenging models and problems. And then kind of it's amazing. You can suddenly do things you didn't thought was possible, and this is kind of way eye-opening thing. And that point about this computation stat, you you separate these two kind of processes. You can do it if you can build a model. You can do inference. You don't need to worry about these things. So this is the whole idea. So this is what we do here in the Bayesian class here, because there is no point to having a theory on Bayes at that level. No, first I need to get exposed to what kind of opportunities this kind of this way of thinking and this way of doing inference and this way of having all this ready software, the opportunities this kind of creates today. Yeah, the machines we're using, the computers, they are just a tool. We should use it. Yeah.
All right, thank you. One more question. Is it okay?
Yes.
So is INLA is an alternative to MCMC for fitting Bayesian models?
Yeah. So this is like a non-MCMC way of doing this. Yes. So within this class of models that we're looking at, we don't actually need to do MCMC. The MCMC will do it. It will do things slower, and in most cases, it will do it worse. In the sense that the Monte Carlo error will be much larger than the actual deterministic error we are making. So actually, we can go better off doing a method that is not 100% exact, but it's almost there, instead of doing that is on average exact, but the error is too large. And that's the point. This is an inherent property of Monte Carlo. It's very easy to get a rough estimate, but if you want more precise estimate, it's very costly. So every digit you want more accurate will cost you 100 times more computations. So if you can get a rough estimate, let's say you used 1 hour to get okay. If you want one more digit, it will cost you 100 hours. If you want 2 more digits, it will cost you 10,000 hours. Okay, computing. So every digit will multiply the cost with 100. So this is getting very, very consuming. There's nothing wrong with all this thing. It's a feature. This is how it is. Is it good? Or sometimes it's not so good, but there is nothing we could do with it. This is how it is. There is no drawback about Monte Carlo. It's a good thing. You can get a very good estimate. You have 3 samples. You can get an estimate for the mean and variance. Okay, amazing. The point is that you want accurate estimate. It's very hard. So this is like a built-in feature. This is how it is. Yeah.
All right. Thank you so much.
Okay.
Yeah. Thank you, Professor Rue, for answering this question and for the great presentation. It was a pleasure to have you with
Thank
us.
you.
We hope we can collaborate again with you next time.
Okay, very good. Thank you so much.
Thank you all for attending. We hope you have learned and enjoyed this webinar. See you next time. Subhanakallahumma wa bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Yeah, thank you.
Thank you, Profesor.
Thank you.
Terima kasih.
Thank you.
Thank you.
Syukron.
Dr. Lubna, terima kasih.
Bu Indira enggak temanin ya.
Pak Al sebagai co-host, silahkan.
Nah, bubar gerak ini gimana? Terima kasih Bapak Ibu atas partisipasinya. Insya Allah sertifikat menyusul dan materi mohon Bu Indira dikoordinasikan materinya supaya juga dibagi ke peserta dan teman-teman yang mungkin tidak sempat. Oke, terima kasih. Spesialnya Bu Dekan, terima kasih sudah on dari awal sampai akhir Bu Dekan. Terima kasih.
Insya Allah. Terima kasih Bu Dekan.
Pak Irfan juga tuh yang standby di ruangan.
Alah, Bapak.
Enggak, saya dengar suaranya Bindira ternyata rocet juga kalau di Zoom ya. Padahal di ruangan sepi ada suaranya, di mulut, di dalam perut aja ketawanya.
Terima kasih Bapak Ibu yang di luar UIN Mataram sudah bergabung. Semoga lain waktu bisa berjumpa.
Bu Juli, Mbak Juli.